Let us try to obtain equivalent integral form of some more differential equations. Now here we have this differential equation a d square u by dx square plus q equal to 0, and if you remember this equation, this is nothing but this is a differential equation governing differential equation of bar. And let us try to see, if I use the Euler Lagrange equation for this governing differential equation of bar, what equivalent integral form do we get, or what will be the nature of the equivalent integral form when I apply the Euler Lagrange equation to this governing differential equation of a bar. Now we have seen that the the Euler Lagrange equation is given as df by du minus d by dx of df by du dash plus d square by dx square of df by du double dash equal to 0. This is the governing differential, this is the Euler Lagrange equation which we had derived, and I'll be using this equation I'll be using this Euler Lagrange equation on this governing differential equation to obtain its equivalent integral form. Now for some reason I will have to slightly modify this equation in order to apply this for this governing differential equation of bar. Now if I rewrite this governing differential equation, I can rewrite this as ae d by dx of du by dx plus q equal to 0. So if I compare this equation with this Euler Lagrange equation, I can see that this d square by dx square will not be applicable here, so I may straight away neglect this. But then for some reason I will have to slightly change the signs of the remaining terms. That is, what I will do is I will take this Euler Lagrange equation in this form: d by dx df by du dash minus df by du equal to 0. I will consider this as my modified Euler Lagrange equation in order to apply this to governing differential equation of bar. Now if I compare this equation with this, what do I get is I get d by dx df by du dash is equal to ae d by dx du by dx, right? I can compare this with this equation, and then also I can compare this minus df by du is equal to q. And as we had seen earlier, I can integrate this equation with respect to dx on both the sides, which will give me df by du dash is equal to ae du by dx, which I can further write it as u dash. And further, since I want to find f, I will have to again integrate this with respect to du dash, which will give us ae u dash square by 2. Right, so this is one term which we get, and on this side for this equation, I get f equal to minus q into u. So what do we do now? We know that the Euler Lagrange equation give us the equivalent integral form in this fashion for some domain of from x1 to x2 f dx, right? We write the equivalent integral form in this fashion. It is integral of f over some domain from x1 to x2 dx. Now here the domain, we can take it as x varies from 0 to L. If this is our domain, then our equivalent integral here will be equivalent integral I will be from 0 to L. We have f as ae by 2 u dash square u dash is nothing but du by dx square minus q into u, and this whole term multiplied by dx. This is the equivalent integral form for our governing differential equation of a bar subjected to distributed load Q. This is our distributed load Q, if you remember, right? So this is what we get. This is what we get. Let us try to apply again this Euler-Lagrange equation to this equation. This was our first example. This was our first example. We try to use the Euler-Lagrange equation to one more example. I'll take one more example, that is EI d raised to 4v by dx raised to 4 minus q equal to 0. And now if you are familiar with this equation, this is nothing but this is governing differential equation of beam, right? This is the governing differential equation of beam. You must be more familiar with this equation. EI d square v by dx square is equal to m, that is moment. And then if I differentiate this once, I get EI d cube v by dx cube, which is equal to dm by dx, is nothing but shear force. If I differentiate this once with this moment with respect to x, I get shear force. And then further, if I differentiate this one more time, then I will get this as dv by dx is nothing but q, which is again the uniformly distributed load. And if I bring this here this side, I get this equation. I get this governing differential equation of a beam. Now suppose say again a beam varies from length say 0 to L. Then let us see, if I apply the Euler-Lagrange equation to this governing differential equation of beam, what do we get? What do we get? So again, what was the Euler-Lagrange equation? df by du minus d by dx of df by du dash plus d square by dx square df by du double dash equal to 0, right? Now again, there the time while deriving this, our variable was u, but here the variable is v. So let me modify this Euler-Lagrange equation. We will term this as v df by dv, df by dv dash, df by dv double dash, right? And now let us try to apply this Euler-Lagrange equation on this governing differential equation of beam. So first let us rewrite the governing differential equation. We can rewrite this governing differential equation as d square by dx square d square v by dx square minus q equal to 0. Now if I compare this governing differential equation with Euler-Lagrange equation, this term has d square by dx square with this, which is similar to this term, and here there is no derivative which is similar to this term. That means this term d by dx, df by dv dash will not be used here in this equation. We can neglect this. And then comparing these two equations, we get d square by dx square df by dv double dash is equal to ei d square by dx square d square v by dx square, right? And then also we get the second equation, df by dv is equal to minus q, Now in order to, our aim is to find f, and in order to find f, first we'll have to integrate this equation on both the side twice with respect to dx in order to remove these terms, right? With that we'll get df by dv double dash is equal to ei, and this d square v by dx square, this is second derivative of v, which we can very well write it as v double dash. Further integrating this with respect to dv double dash, I get f as ei by 2 v double dash square, right? And then here this equation gives us F is equal to minus QV. So further, we have already seen that the equivalent form by Euler-Lagrange equation is of this form, is of this kind, right? Now here again the domain is, for our problem, the domain is from 0 to L, and what is F? We get F as EI by 2 V double dash square minus QV dx. So this is the governing, this is the equivalent integral form of beam, and this is the equivalent integral form of bar. Now if you look at this terms carefully, right, I can rewrite this as this, I can rewrite this equation as integral from 0 to L A E du by dx the whole square dx minus integral 0 to L QU dx, right? So this is nothing but we call this term as potential functional. This is the strain energy of a bar, and this is the work potential. This is the strain energy, and this is the work potential. Similarly, if I look at this equation carefully here, if I rewrite this equation, I get this term as integral 0 to L EI by 2 d square V by dx square the whole square dx minus integral 0 to L QV dx. And again, this is nothing but this is also the potential functional, which we generally denote by pi, is nothing but this is strain energy of a beam, and this is the work potential term, and therefore pi is equal to strain energy minus work potential. And even here we get, in similar fashion, we get this as pi equal to strain energy plus work potential. So what do we conclude from here is, if I apply the Euler-Lagrange equation to the governing differential equation of any structural problem, this equivalent form will be always in this fashion: pi is equal to strain energy minus work potential. This will be our potential functional. This will be our potential functional. So for structural problems, we need not start our problem from its governing differential equation, but rather we can directly start it from here. If we know the strain energy and work potential of any structure, we can directly start to obtain the solution for those problem right from this step, and this procedure is called as Rayleigh-Ritz method, wherein we directly start solving the structural problem from this step, wherein we write the potential functional as strain energy plus work potential. But usually this work potential is negative of work done. So further we can also write it as strain energy minus work potential.